Okay, let's go ahead and start um, just with kind of the formalities here. The test will be Monday, right? And then so that's the third test, and then the following Monday is the final exam. Um, I have already now posted the answers for the sample test. So I put those up this morning. So those are on the Blackboard page. But I think since we're a little pressed here for time on these last homeworks, um, we'll just limit the test number 3 to problems like the first 10 problems from the sample test. So that does not include polar coordinates on test number 3 or what we're going to talk about today, which is triple integrals again. On test number 3, but those are on the sample test. But we'll defer those to the final exam the following week to give you more time to practice on those. So that means only from the sample test, only the first 10 problems would be the material for test number 3. So not polar coordinates or not triple integrals. So in other words, not these 2 homeworks, right? Okay, but all the homeworks that have already been due prior to this might be on test number 3. See, something else I was going to say. Oh, so I did post the solutions to the sample test, including those last few problems that aren't going to be on test number 3. And then I will record again a video where we just review some of the key problems from that sample test, but you already have the solutions. So I'm simply going to be explaining the solutions that are already on the sheet on that video, just like we did for the first couple of tests. So I'll probably do that. I'll probably record that tomorrow. So it'll be, posted late tomorrow or maybe Friday. So I'll send a notification when that video is posted. So it'll be on the link will be on the Blackboard page, in that sample test folder where the solutions to the sample test are. Okay. And this test works and the final exam works the same way, right? You can, of course, bring your calculator and the index card, right? Your survival card, just like on all the other tests. I think now we'll say more about the final exam on Monday. Probably there will be a review sheet for the final exam. So I probably will make one out, like a sample final exam for you, but it won't be posted until Monday will be the earliest. And then I think on Wednesday, which is not a class day, that's a reading day, we will have a optional review session. That's not a class day, so you're not required to come, but an optional review session that day on Wednesday, but it'll have to be a little bit earlier. So it'll have to be at 10. So I've asked to reserve the room, but they may change the room on me if this room is not available. Hopefully they would just give us a room next door or something. But I should know that by Monday. So again, on Monday, I said more about the the details of the final exam. Now some of you are maybe eligible not to take the final exam, depending on your test number 3 score and what your homework comes out, right? And what your homework average turns out to be and what your attendance is. So some of you will earn enough dollars, I think, to or you're at least on the on the trajectory to earn enough on the vector, let's say, to earn enough dollars, right, to not enough flux dollars to not have to take the final exam. So I will say more about spending your flux dollars also. Okay, so that's easy to do. You just fill out a sheet of paper and that's it. But so we'll talk about how you're gonna communicate that to me on Monday, since we don't have class again after next Monday. Okay, I think I said all of the pertinent stuff there. Do y'all have questions about the test on Monday? So the first 10 problems from the sample test. So really what that covers is there's really only two things. It covers finding extrema for surfaces, right? Functions of two variables. So don't forget the really difficult thing to remember there. So something to include on your index card would be that second partial derivative test, right? Okay, where it has that sort of complicated calculation where you have to compute that value d, right, and then use that to determine if a critical value, is a maximum or a minimum or a saddle point, or maybe neither. And then also double integrals, right? So finding volumes with double integrals, or possibly finding areas of regions on the XY plane using double integrals. And then maybe also finding the average value of a surface, remember, which is the average height of a surface, or the average value of a two variable function. Remember, that's just you compute the volume and divide it by the area of the region of integration. Okay. So I think there's a problem like that on the sample test. That's really it. Okay. So it's not a lot of material, but those problems are those are complex problems, right? Each problem can take a little while to work through, right? So you definitely need to practice that before you come take the test. All right. So again, do y'all have things you want to clear up here before we commence? We're going to talk a little bit more about polar integrals, and then say some more about triple integration. Just a little bit. Those triple integrals are, you'll see in certain cases, are pretty easy to set up. It seemed like they might be complicated, but actually they're not that bad if you know the shortcut, which I will show you, which is also described on the solutions to the sample test. Those last couple of problems from the sample test on triple integrals has kind of an explanation of how you can sometimes take a shortcut to set up a triple integral to find a volume for a three-dimensional object, right? A solid in 3 dimensions. Okay, let's open first here let's open this polar coordinate homework. I wanted, just as a warm-up, to do one of the problems from this one, and then we had one more polar example in our notes, and so I want to finish that example, and then we'll talk about triple integrals, and then if we have enough time at the end, we'll come back and look at some more of these homework problems from using polar coordinates to do double integration. Let's look at problem number 6 here, I think. Okay. Oh, all right. So this is kind of a straightforward problem in a polar integration. This is just kind of a vanilla problem for this homework, or what you might see on the test. So it says evaluate this integral. So that is in notice that is given to you, of course, in rectangular coordinates, right? Because the variables are x and y, but we want to convert it to polar coordinates, and so compute this. Want to compute this this integral using polar coordinates, and that might be kind of a challenging integral to carry out in rectangular coordinates because of the nature of the integrand. But if we convert this to polar coordinates, maybe that will make it easier, all right, to actually compute this or evaluate this double integral. So they're giving you a bunch of boxes to fill in, right? That is, making the conversion from rectangular coordinates to polar coordinates, and then they actually want you to evaluate this double integral in polar coordinates, and then write down, exactly what what the value is, right, for that double integral. Apparently it's going to come out kind of messy because they want you to round it to 4 decimal places here at the end. All right. So do y'all have that? Can y'all write that down for me? I'm going to switch here to the notes, so I have a little room to work. So let's let me scroll down here. Here we go. And let's write down what the original problem was, right? So I think it was what we wanted to go from -5 to 5. Those were the outer limits of integration, right? So so those are pretty easy, but but the limits of integration for the inner integral, that was a little bit worse, right? Was it 0 to something like square root of 25 minus x squared? Okay. And then we had cosine of something. Was it square root of x squared plus y squared? Oh, just x squared plus y squared? So cosine of x squared plus y squared. And then I think had to be dy dx, right? Okay. So so let's see if we can convert this now to polar coordinates. So the place I would start there is to try to figure out what the region of integration looks like, right? So you want to look at the region of integration and then try to convert that to polar coordinates. Okay, so you can get the limits of integration in polar coordinates, right? Remember, when you convert this to polar coordinates, you're going to have limits of integration written in polar coordinates, right? And usually the order of integration for the polar coordinates is going to be dr d theta. Okay. So let's see what this region of integration looks like. So remember, this is for the inner limits of integration, right? This is 0 to and to this curve, right? Just set the 25 square root of 25 minus x squared equal to y. And so let's figure out what this curve looks like. All right. Okay. So we can, yeah. So if you write that, and then get rid of the square root by squaring both sides, right? You would get 25 minus x squared is equal to y squared. And then if you bring the x squared over, right, you get x squared plus y squared equal 25. And then you can see that's going to be a circle, right? Because this is x minus 0 squared is x squared, right? And y minus 0 squared is y squared is equal to 5 squared. So so that curve is really a circle with radius 5. Okay. However, we were only interested in y being the positive square root of 25 minus x squared, right? So that means that we're only dealing with the upper half of we're only going to deal with the upper half of the circle. And the radius here is 5. I didn't quite draw my axes here big enough before class. So the radius there is 5. So this curve, right, looks like the top half of a circle. And you don't have to draw it beautifully. And I'm certainly not going to draw it very nicely, right? Okay. So remember, a y there, right? Okay, is ranging from 0 up to this curve, the square root of 25 minus x squared, and then x is going to run from -5 to 5, right? So that's going to be from the from the left x-intercept of this semicircle, right, to the right x-intercept of that semicircle. This is -5, and this is 5. So our region of integration is this. So that's what we want to see if we can describe in, that's what we want to see if we can describe in polar coordinates, right? Okay. So let's see, what would that look like in polar coordinates? So what are going to be the limits on the radius, right, for points in this semicircle? How far are these points away from the, how far are these points away from the origin? Any of the points in this region? That less than 5, right? Okay. So you can describe that region, right, as points having what radius less than or equal to 5 and greater than or equal to 0. But so it looks like for our limits of integration, right, we would just have from 0 to 5, right? Now, what about for the limits of our angle? Here's where you have to be careful, okay? Because what about for the angle of the points here in this region? So if you pick out a point here and think about its polar coordinates, right? You know its radius has to be less than or equal to 5, right? Because you've got to be inside the circle. What about its angle? So 0 to pi, right? Okay. So don't go 0 to 2 pi, because if you go 0 to 2 pi, right, you're going to get the whole circle. But we only want the top half of it, correct? Okay. So it looks like this is, it's like this is 0 to pi. Okay, now you also have to take your, rectangular function, right? Okay, and you want to convert that also to polar coordinates. How do you do that? Well, that in this case, Robert, you're right. That's the fast way. All right, okay. But in general, how do you? So we do have a little shortcut here because this expression is x squared plus y squared, right? Which we know secretly is what? That's really r squared, right? Okay. But in general, you may not have that shortcut. All right. You may just have some formula involving x and y. So how do you convert that to polar coordinates? Yeah, right. So you just make this substitution, right? X is equal to r cosine theta, right? And y is equal to r um, sine theta. Okay, so you're going to have cosine of, I don't know if I can squeeze all of that in. So you're going to have cosine of this squared, right? R cosine theta squared plus r sine theta squared. But in this case, it turns out if you simplify that, but in this case, it turns out if you simplify the r cosine theta squared plus the r sine theta squared, you will just end up getting r squared, okay? Because you can factor an r squared from both of these terms. That would leave you with r squared times cosine squared plus sine squared, but cosine squared plus sine squared is 1, right? So you end up here with just cosine of r squared. What's the other factor, though, now that you have to include in the integrand? Yeah, that's right. An extra factor of r, right? So don't forget that. So let's squeeze that in. Let's squeeze that in also. So don't forget that must be here. And that's going to be that turns out to be really useful in this situation. But to have that extra factor of r. So let's see. I have cosine of again, all of this inside the parentheses just simplifies to r squared. So I have cosine of r squared and then times r and then dr d theta. All right. So let's worry about now. Let me extend it over there. Let's worry about that inner right integral. So we're integrating a cosine, right? But so generally when you integrate a cosine, what's the antiderivative of cosine? Pretty easy, right? Just what? It's just sine, right? Okay. But unfortunately, this is not just cosine of r, right? This is cosine of r squared. So we're going to have to do a little bit of substitution. All right. So let's let u be r squared. Then what is du dr? That's going to be 2r, right? Or dr is going to be what, du divided by 2r? So we fill that in our usual substitution manner, right? And we get cosine of u. That's nice because then I know how to integrate, right? And then times this r is still here, right? And then times dr, but dr is du over 2r. Oh wow, how convenient! Because what's going to happen to the what's going to happen to the r's there? They're going to cancel, right? So you see that extra factor of r turned out to be really useful there. Because it cancels with that du over 2r, right? And I end up with just cosine of u du, which I know how to integrate. But we do need to factor out the 2 in the denominator. So let's factor out a 1/2, right? Outside of the inner integral. So I just have cosine u du and then d theta. Don't worry about changing your limits of integration because we're going to switch this back to r here in a minute, right? So how does that integrate? Y'all just told me. That's sine of u, right? So that integrates as sine of u, and we have to evaluate that from 0 to 5. But before I evaluate it from 0 to 5, I need to switch back to r, correct? But what was u? That was r squared, correct? So I have 1/2 sine of r squared evaluated from 0 to 5. So that's not too bad. What does that work out to be? Can we do that without, can we do that just by inspection? Because what is, when you plug 0 in here, you get sine of 0 squared, but that's just sine of 0. But of course, what's sine of 0? Yeah, that's really convenient. So all you're going to get left with here is what you get when you plug the 5 in, which is sine of 25, right? So we have 1/2 sine of 25, and now d theta. I guess the 1/2, if you want to, you can factor that out also. But it's really easy to integrate sine of 25 with respect to theta, correct? Because this is a constant, right, with respect to theta. So what's the antiderivative there? Yes, sine of 25 theta, right? Or I guess we could write theta times the sine of 25. And that would be evaluated from 0 to pi. But now, when you plug in, of course, when you plug in 0 for theta, right, you're going to get 0, right? And then when you plug in pi for theta, well, you just get pi. So I guess this turns out to be something like pi over 2 times the sine of 25. Okay. Did I do that right? Not so bad. Kind of a weird number, but okay. Yes. What now? Oh yeah, did I mess that up? No, no, no. I'm not integrating sine, right? Because this is just a constant with respect to theta, right? So whatever that number is, it's like a 3, right? Okay, so you're just going to get theta multiplied by that. So right, convert that to 4 decimal places with your calculator, and type that in. I don't know why they didn't want the exact answer, because the exact answer is not that bad. Okay. Now let's take one that's a little bit trickier. So here we're not looking for we're not looking to compute a volume. That last answer was actually the volume beneath that surface, cosine of square root of x squared plus y squared, above that semicircle. Okay. So you could interpret that previous problem as a volume, but this is not a volume. This is just an area we want to calculate. Okay, and it's the area inside of this 3-leaf rose. Okay, or it's like described as a clover. It's this 3-leaf clover. So that shaded area is what we want to. That shaded area is what we calculate. So it's an area in 2 dimensions, not. We're going to, however, solve this just like we solved areas in, just like we found areas in 2 dimensions in the rectangular plane, right? Using double integrals. And remember, the trick is you're going to use an integrand of 1. Okay, that's the that's how you solve this. And all you have to do is write limits of integration here that describe your region of integration properly. Okay, so if you can write limits of integration on the double integral that describe the region of integration correctly, and then integrate here that integrand of 1, then you will have the area of this have the area of this region. So the only real difficult, well, the 2 difficult parts of this problem are first describing that region of integration using, and we want to do it with polar coordinates, and then actually evaluating the double integral, because that might be tricky as well. Right? So let's see if we can figure out how to describe that. Let's see if we can figure out how to describe that region inside that region inside that 3-leaf clover. First, what do you know about points on the 3-leaf rows themselves, on the curve itself? They satisfy this equation. Okay, so for points that are exactly on the curve, like this one, right? You know that the R value is exactly equal to, so the radius value is exactly equal to 3 times the cosine of 3 times the angle theta. Okay, so for points inside of the curve, right? How do we get points inside of the curve? Just do what to your equation? Same thing that we did a moment ago when we were doing this problem, right? Okay, see, points on this circle, right? A point on this circle, its radius value is exactly what? 5, right? But we were interested in points inside of the circle, correct? So we set up this inequality, right? We took the radius value less than or equal to 5. Okay, the same is going to be true here. All right, exactly the same will be true here. All right, just set your upper bound on your radius to be 3 times cosine of 3 theta. Okay, but also, of course, you want the radius to be bigger than or equal to 0. So your inner limits here of integration are well, they're not simple, but at least we can write them down. It's going to be 0 to 3 cosine of 3 theta. Okay. Now, the tricky part here, however, is the angle. Okay. All right. So what is theta what does the domain of theta have to be, right? How large and how small does theta have to be so that we can get this full 3-leaf rows? Okay. Yeah. So, usually a safe bet will be 0 to 2 pi, okay? Because, of course, that the period of cosine, right, is 2 pi, right? So you're going to cycle through, all possible values for the cosine, right, if you go from 0 to 2 pi. Another way to think of this is, well, this leaf is this 3-leaf rows, right, is a closed curve, right? And if you sort of thinking about tracing that in walking around, right, that entire 3-leaf rows, right? Notice your angles they would encompass all angles from 0 to 2 pi, right? Because you're sort of, moving through every quadrant here, right? Okay, with this curve. However, that unfortunately is a little bit too big. Okay, you don't really need to go all the way to 2 pi to draw you do want to start at 0, but you don't need to go all the way to 2 pi to draw the entire curve. Okay. The problem is the 3. All right. Cosine of 3 pi does not have period 2 pi. Okay. So because of that extra factor of 3. So that has that's changed things a little bit. Now you can do it, but it's not a trivial task to figure out what is the proper domain or theta to trace out the entire curve. Here, experimenting helps a lot, though. Okay, so so in your homework, let me switch back to the homework. I have given you a tool for doing polar graphing, and in your homework, at least, you may want to make use of this tool. Let me see. There's the link, okay, for basic polar graphing. So if we click on that, see, we're going to get this nice Desmos page here, right, where we can just fill in a curve here, right? And let's see what we get. So let me see if I can type this with if I can get the keyboard to come up here. Don't want that one. Yeah, well, that's what, not quite. Okay, it's a little bit more complicated than that, unfortunately. So let's see, we want 3 cosine of 3. So that's it, right? So notice that there we got it already. The entire there we got already see the entire 3-leaf rows. But notice that Desmos actually adjusted this for us. We're using a domain of 0 to what? Only pi is necessary. Okay. So if you go from 0 to pi, you get the entire rows. Okay. Now, if you go bigger than this, that's okay. All right. In terms of graphing, that's all right. Let me type in 2 pi. So see if you do 2 pi, it's just going to trace it out twice. So you see the same curve, okay? All we've done here is plot each point 2 times, all right? But it's not necessary to go to 2 pi. 1 pi will 1 pi will suffice and also get the same curve. So on your limits of integration, you want to stick from 0 to pi. If you do a little bit less than this, what did you suggest there, David? 2/3? Yeah, let me show you what happens. Yeah, sadly you don't get the entire thing. Okay.
So, thing.
Huh?
I don't understand how to possibly explain.
Yes, you okay. It's not easy to explain, so I'm not sure I'm going to explain it well. Here is why. You want to make sure that you what are your what output values do you get for cosine? Plug in cosine. It um yeah, no, what's the minimum? Now when you plug in an angle into cosine, what's the minimum value? It's minimum output. -1, right? And the maximum is so you want to pick a domain that you make sure cosine goes from -1 to um, but if you yeah, and 0 to pi will do that, right? Okay, because at 0 it's at 1, and at pi it's at -1. Now, but you also have to make sure that so also have to make sure though that you get all angles. Want to get a full revolution of it. So that would be 0 to 2 pi. Well, notice if you plug from just 0 to pi into this formula, right, David? Notice what's happening. You're going to get all output values from 1 to -1, right? Yeah, that's right. And you're getting all angles from, at least all angles from 0 to 2 pi because you're multiplying here by 3. So since you're multiplying by 3, if you go from 0 to pi, you're actually going up to 3 pi instead of 2 pi. So you get a full revolution of angles. That's how I think of it. But that's not that's something you have to think of. So the experimentation here is nice. All right. Okay. So let's fill that in. If you did 0 to 2 pi, if you went from 0 to 2 pi, that wouldn't be the worst mistake in the world. You would just get double the area. Okay, you would just end up getting double the area. So all you need here is really 0 to pi. This is an example from the book, by the way. So if you look at polar integration, this example in the book, but you're not going to like the example, the way they explain the example in the book. So because what they do is try to figure out the area of one leaf and then multiply it by 3. Okay, and that's fine, but then you have to figure out what angles to use to get just one leaf. So that would be an angle between here and here. And it turns out to be that's minus pi over 6 to pi over 6, but that's not easy to figure out either. So I don't like that. Okay, I think it's easier just to go from 0 to pi. Whew. All right, now let's see if we can actually carry out that integration. I'm not even sure we can do that. Let's see what happens there. All right, so well, it's certainly easy to integrate, get started there. Oh, don't forget, you need the extra factor of r, though, right? Okay, your integrand is 1, but don't forget you also need the extra factor of r. So that must be there. So let's see, how does well, what is the antiderivative of r? Darn it, what? R squared over 2, right? So let's throw that in. So we get r squared over 2, and then evaluated from 0 to 3 times cosine of 3 theta. So let's factor out, let's factor out the 1/2. Okay, right? So get that out of the way because that's going to be annoying. So let's see if we can get rid of that. And that we can factor actually all the way in front, right? So we can put the 1/2 in here. And then we just fill in 0 and 3 cosine of 3 theta, right? So fill that in for r. So that gives us what? 9 cosine squared of 3 theta? That's ugly. And then, but when you plug 0 in, that's a lot better, right? Because you just get 0. So I have here a 9 cosine squared 3 theta, just d theta. Guess I don't need this bracket. Well, the 9 is annoying also, so we can factor that in front. So it looks like we're going to have 9/2 here in front, right? And then we have to find this antiderivative for cosine squared of 3 theta. All right, so we've seen, I think briefly already, an example with cosine squared in it. This comes up frequently, though. Well, at least once or twice. It's come up in the examples, but it's also going to come up in the homework on how to find the antiderivative of cosine squared. Okay, but remember, you're going to use this. You're going to use this famous identity that's really helpful for cosine squared. If you have cosine squared x, remember that's 1 plus cosine of 2x over 2. So you can eliminate the square on that cosine. Now you still have some work to do there, but at least you won't have a cosine squared. So we have 9/2, and then integral from 0 to pi of, let's see, this would be, so when I apply this identity to cosine squared of 3 theta, I get what? 1 plus cosine of what? 6 theta, right? Because you're going to double the 3 theta here, right? So you get cosine of 6 theta and then over 2, right? So let's see, I can factor out another 1/2, right? So it looks like I have 9/4 here in front. And now I'm left with just trying to figure out the antiderivative of this, correct? Well, I can certainly find the antiderivative of 1 with respect to theta. What would that be? Theta, right. Okay. So let's break this up. So I have 9/4, and then this very simple integral. I know the antiderivative of 1 is just theta, right? And then plus, here's the tricky part. So I still have this 9/4, 0 to pi of, and then cosine of 6 theta. All right, so how would y'all attack that, finding the antiderivative of cosine of 6 theta? Looks like that's going to involve what? What now? Yeah, another substitution, right? Okay, because I can find the antiderivative of cosine of just theta, right? That's pretty easy. fact, we've already done that, right? The antiderivative of cosine of theta is just sine of theta, right? But here I have 6 there thrown in. So let's do a substitution. But this is a very simple substitution. So we're going to let u be 6 theta, which means du d theta is, of course, what? 6, right? Okay. And now, so that means then that d theta is du over 6. Of course, this one we can do anytime we want to. That one is very easy. So here we have 9/4, 0 to pi, cosine of u, and then du over 6, right? Factor out the 6, the 1/6. I should have left the fourths factored out. Let me leave that as 9/4 times 1/6. So I'm not going to actually, let's not multiply those together. And then what? Antiderivative of cosine of u, right? Du. But that we know what that is, right? That's just sine of u. And then we can just substitute back in. Then we can just substitute back in the fact that u was 6 theta, right? So let's see. So I have 9/4. Let's see here. The antiderivative is just theta. And that's evaluated from 0 to pi. And then I have 9/4 times this 1/6. And all of this is going to be sine of what? Sine of u, but u was 6 theta. Is that correct? Also evaluated from 0 to pi. Well, let's see, if you do this one, when you plug 0 in for theta, of course, that's going to be 0. So all you're going to get is when you plug the pi in. So you have 9/4 times pi plus, and then we have the 9/4 times the 1/6 times, let's see what we get what do we get when we plug stuff in here? Is that too easy? Yeah, you get sine of 6 pi, which is which is 0. And when you plug 0 in here, same thing, you get sine of 0, right? Oh, so it looks like all of this is just going to be 0. Oh, how convenient there. So I just get, is that just 9/4 pi? There we go. I think that's it. So would have guessed that area of that 3-leaf rose there is just 9/4 times pi. Okay. Let me show you now. We're going to come back and do some maybe some of the other homework problems from the polar integration if we have time. But I want to show you how to set up now triple integrals. Okay. The first one that we're going to look at is, this is kind of a complicated version of triple integrals. We're not going to try to evaluate the triple integral, but then I'm going to show you how in certain situations it's easier to set up triple integrals. All right, here's what we want to compute. We want to find the volume of this barrel. Okay, so the volume of that barrel, starting at -2 on the z-axis and going up to +2 on the z-axis. All right. So here's the formula for there's the formula for the barrel. All right, so it's one of our no, I don't think that is one of our quadratic surfaces, but maybe it is. Okay. So anyway, that equation is the definition for barrel. All right, now here's the way I was explaining how you could integrate this before in one of the earlier examples. All right, so let's take a look at just a trace of the barrel here in the XY plane. All right, so what is this curve, right? What is this curve that's in the what's this curve that's in the XY plane? Okay. So how do you find that? The formula for that curve that's the XY plane. Set z equal to 0, right? Okay. So in your formula, just set z equal to 0. So let's do that very explicitly. So we have 4x squared plus 4y squared there, right? Plus what, 0 squared, right, is equal to 16. And now if you just divide everything by 4, you get this really simple curve, right? You have x squared plus y squared equals to 4, okay? And of course, that's the equation for what? That's a circle, right? Okay, with radius 2, okay? Centered at the origin with radius 2. So just exactly what we're seeing there, right? What we're already expecting to see is what we get, right? X squared plus y squared is equal to 4. Now, how do we compute the area, though, of that circle, but using double integral? So I want to find the area of the circle, but using a double integral. Of course, I can compute the area of that circle easily, right? With just the formula from geometry, okay? And b, what's the area of that circle? It's pi times the radius squared, right? Okay, so we don't need a double integral to calculate the area of that circle, but let's calculate the area of that circle using a double integral. So you remember how did you do that? All you have to do is remember, all you have to do is really just write down limits of integration that describe your limits of integration, right? That describe your region of integration, correct? Okay, and then integrate that using what as the integrand? No, the trace is going to help you find the limits of integration, but what is the integrand? What is the expression that you integrate when you're computing a region? Area of a region, 1, right? Okay, so you're going to calculate the area here. Let's draw it. To calculate the area here of this just this circle in the plane, right? Okay, where that barrel intersects the XY plane, you'll just set up a double integral with integrand of 1. You don't have to multiply by r because we're not using we're not using polar coordinates here, right? Okay. Although it would be easy to do with polar coordinates, right? Because that circle would be easy to write down. It would be easy to describe that that disk, right? It would be easy to write that. But we're going to do it with rectangle, right? So how do we describe that region of nation? Let's see. Y'all want to? How do you want to do it? You want to fix I first, and then fix a y value first. Fix an x value first. Let's fix a y value first, right? So let's just choose a specific y value. There's a specific is that a specific y value? Yeah, there's a specific y value, right? And think about how x is varying, right? When you pick a specific y value. So in other words, you're going from this side of the circle right over to this side of the circle. In other words, what's the formula for this side going to be? What's the formula for this side going to be? How do you figure that out? Just take this equation and do what? Is that equal to y? No, we're fixing the y, right? Okay. And the x is what is going to vary there. Yeah, that's right. Solve the equation for x. Solve the equation for x. So you would get, this is pretty easy to solve for x, right? You get x is what? Plus or minus the square root of 4 minus y squared? See, positive square root of 4 minus y squared is this half of the curve, and negative is this half of the circle. And remember, you want to go from this side to this side if you're fixing a value for y, right? You're moving from x here to x here. So this is, so it's going to look messy. You're going to have minus the square root of 4 minus y squared up to positive square root of 4 minus y squared. And this is dx. Now, what does, so what did, now, how's y going to vary? From -2 to 2, right? Okay, you can see that, right? So you're going to cut one of these slices just like I've shown here, right? From -2 to 2. Elijah, how would you find that though? You can see it easily on the graph here, but how would you actually discover it was -2 to 2? What would you do with this equation? Set x to 0. Okay, see, along the y-axis there, x is 0, correct? So if you set x to 0, you can find out how far you're moving from this side to this side, correct? If x is 0, that's along the that's along the y-axis. So just set x to 0, and you would get what? Y squared is equal to 4. And then solve that, you get y is plus or minus 2. Oh, so you're going from -2 to +2 here. Well, that's it. Okay, so there is the area of that disk. Okay, what is that going to turn out to be, by the way, when you integrate that? We know how to compute the area of that disk. What is the area of that disk? Because that's a circle, right? So what is it, pi r squared? Yeah, it's going to turn out to be 4 pi. Oh, guess what? All of that turns out to be, at some point in the future, if we were able to evaluate that, we would end up. Okay. Now, what does this have to do with the volume, right? Okay, because all I've done is find, now all I've done is find the area of this. But how does the variable form? That's right. The barrel is formed by stacking a bunch of these discs on each other. Okay, is that how the barrel is formed? The barrel is formed just as a bunch of these discs stacked on each other, right? So, find the volume. What we want to do is find the area of each one of those discs, correct? And then do what? Begins with an I. Integrate, right? Then want to integrate areas together. From where to where on the z-axis there, things. You can see it's got to be -2 to 2, right? Okay, from -2 up to 2. We had to be told that, by the way, okay, because this surface continues further up, right, and also goes further down. I think that was part of the instructions of the problem. Oh yeah, right. We only want the burial from -2 to 2. So we're going to end up, finally here, we're going to end up with a triple integral that looks much like this one. You're going to integrate this double integral from -2 to 2. So notice, what's your order of integration going to be here? You're going to have 1 as your integrand, and then you're going to have dx, dy, dz. The problem, so it would be nice if I could just use these limits of integration. So if I just had, it'd be nice if I just had minus 2 to 2 here for the y, and minus square root of 4 minus y squared up to square root of 4 minus y squared, right? But unfortunately, that's going to be wrong because I'm a little bit too optimistic if I use these limits of integration. If you use these limits of integration, what you are calculating a volume of an object, of a solid, but what would this solid be? You would, in that case, you would be assuming that all of these disks are the same as what? If you integrated like this. That's right, you're a cylinder. You're exactly right, David. You would be finding the volume of a cylinder. Okay, because you would be assuming that all of the disks from top to bottom, we find the area the same way. Okay, in other words, all of these disks from top to bottom have the same shape, but they don't because they get a little bit what? They get a little bit narrow, right? Okay, they change. Oh, by the way, what does this turn out to be? If we did this. So if you're just calculating the volume of a cylinder where you have that same disk all the way up to 2 on the z-axis, all the way down to minus 2 on the z-axis, so the barrel has the same width all the way. Well, volume of that beat. Just take the 4 pi, I think just multiply it by height there. What's the height? So I think you said that was 16 pi. But unfortunately, that's not it. Okay. All right. So how do we get a little bit clever? What we want to do is think about each one of the disks separately. Okay. So let me draw a different disk here. But we're going to use the same game plan. All right. We're going to use the same game plan. All right. We're going to try to calculate the area of that disk. For that disk can be anywhere from top to bottom, not just in the XY plane. That disk can be anywhere from top to bottom. So it could be on the bottom, it could be this disk. And then still integrate those areas all. So we have to think about a little bit more carefully, unfortunately. But we're going to use the same idea. So I'm going to try to find my limits, my proper limits of ratio. Now, remember how we found these limits of integration are in the XY plane or X? Let's go all the way back up. You plugged in 0 for Z, and then what? Solve for X. Problem is, in a disk above or below the plane, Z might not be 0. Z might not be 0. That's fine. Just don't plug in 0 for Z. Just keep Z in, but still solve for X. So see if we can do that. So what was the original equation? 4x squared plus 4y squared plus z squared is equal to 16. Let's just keep the z, where z could be any value, but still solve for x. So let's see, what do we get here? It looks messy, but we can do it there. So we have what? 4x squared is equal to what? 16 minus 4y squared minus z squared, right? Divide by 4 and then solve for x. So you get x is what? The square root of 16 minus 4y squared minus z squared over 4. And it's plus or minus. So those become now, if you want to calculate the volume of the barrel instead of a cylinder, these become the limits of integration for X. Just don't assume Z is 0. Just keep using Z as some value. Now, how to find, what about for Y? So let's open Y from the left hand of one of these discs over to the other side. See if I can draw that properly. So from this side over to this side. Remember how we found it down here, the +2 and -2? What do we do? That's right, okay? We set X to be 0, right? So in this equation, we set X to be 0, okay? And solved. So let's see what we get. If X is 0, we have, so if X is 0, we have what? Well, 4 times 0 squared, right? Plus 4y squared plus z squared is equal to 16. So this term is 0. So we just get what? 4y squared is equal to 16 minus z squared, right? Or y is plus or minus the square root of this. Y is equal to plus or minus the square root of that. So that becomes our second limit of second set of limits of integration. Of course, if z is 0, right, you just get plus or minus square root of 4, which is plus or minus 2, right, which is what we had for the disk on the plane. And now what about z? Don't have to change that. It's still -2, 2. Still -2 to 2. All right, let's see if we can write all this down now. Oh, I don't even know if I have room. All right, so let's see if we can fill all this in. What was the proper triple integral? All right, so z is -2 to 2. What was y? What were the limits of integration on y? Up here, right? So negative square root of 16 minus z squared over 4 up to positive square root of that. And then for x, that was what? Minus the square root of, what was that big mess? 16 minus 4y squared minus z squared over 4. And then just up to the conjugate of that. There's the that is going to be if you integrate that, you end up with, so that's not easy to do by hand, obviously. I think it ultimately turns out to be this 44 pi over 3. So the cylinder we said was 16 pi, right? That's 48 pi over 3. So the barrel turns out to be a little bit less than that, 44 pi over 3, but not much. Okay. The volume of that barrel is very close to the volume of the cylinder. Well, you can see, right? you're just going to be missing a little bit of volume right from the sides, okay, as compared to a cylinder going straight up and down, right? So, whew, but man, that's a mess, okay? That's kind of conceptually tough, right? To figure that out, much less evaluate. Let me show you another one now, and I'm going to show you a shortcut. So we're not going to try to evaluate here, just trying to set them up for the time being. Let's see if we can find this volume. I think we've calculated this volume before, maybe something very similar to this, but using double integral. See if we can calculate triple. So I want just the volume beneath this surface. Surface is z equal x times y, right? But down to above this region, the 20. So this is from 0 to 3 on the x-axis, and from 0 to 4 on 0 to 3 on the x-axis and y-axis. Now that so sorry, I have a lot of things, but here we catch it. If you are looking, if you just want a volume beneath surface down to a region in the xy plane, that's exactly this type of volume, right? Okay, beneath the surface down to a region in the xy. Then set up the triple clutch. Right? And going through that process that previous example. By the way, that previous example is not like this. Okay, this only applies beneath the surface, down to down to a region in the xy plane. That previous volume was not that sort of. Okay, but this one is just there's the surface of this square, right, or this rectangle, the xy plane. Here's how you can set this up really quickly as a triple integral. The order of integration that you'll want to use, though, is this. Use dz first. And then you can either do dx dy or dy dx, okay? Whichever suits you. You'll still use an integrand of 1, okay? Still going to use an integrand of 1 here. For the limits on z, just use 0 up to your surface. So just assume you're going to start in the xy plane and go up to the surface that you're beneath. Remember, these integrals only apply when you're beneath the surface down to the xy plane. Well, what is the height of this surface? It comes from this formula, right? So that's xy. So that is going to be your upper limit of integration. Now, for your limits of integration for x and y, you just use the limits of integration that describe the region in the plane. Okay. All right. So since we're integrating x here first, what are our limits on x in this region? Let's see. X is running from what? 0 to 3. I'm looking at the wrong. From 0 to 3, correct? So just have 0 to 3 here. And what are the limits on y in this region? Y is running from what? 0 to 4. There it is. Oh, there's our triple integral. That's pretty easy, right? But remember, that just applies for what's the situation? Beneath the surface down to a region in the xy plane. Okay, so that special type of volume you can set up very easily there using a triple integral. Let's try another one. So we want beneath this plane this is the plane z equal 8 minus x minus y. So that's plane. Beneath this plane, it's hard to imagine what that volume looks like. Beneath this plane down to this region in xy plane. So this little triangular region in the xy plane. So that's bounded by this line, which is y equals x. That's the line y equals x. And then above, stop at y equals 3. This line is 5. So I drew a picture of the region in xy. There's our region of integration. We want below y equals 3 down to stop at this 45 degrees. So not all the way down to the x-axis. Just stop at the 45 degrees on. So that triangular, this triangular piece right there, is our region of integration. But notice again, we're in this special situation on a volume beneath the surface down to a region in the xy plane. That is easy to set up as a triple. So let's see, what's that going to look like? Well, again, use dz first, all right? And then you can do dx dy or dy dx, it doesn't matter. Let's do, just for fun here, let's do dy dx. What's the integrand going to be? 1, right, okay. So the integrand is going to be 1. What are our limits on z then? 0 to what? The surface, which is what? 8 minus x minus y, right? And now let's see, we're doing y next. So let's see. Let's see. So let's fix an x value. Let's say x equals 1. So what is the extent on the y there? I know where it's going on the top is what? 3, right? Where is it starting at though? X, isn't it starting at x? Yeah, okay, starts at x and goes up to 3. And then what about the limits on x? Now this direction on x, you're going starting at 0, going all the way to what? 3, I think, right? Isn't where these two cross each other? Remember, your outer limits of integration are going to be constants, right? Okay, you may have variables on your inner limits of integration, but your outer limits of integration are always going to be constants. So something like this. Well, that one we could have a stab at evaluating that one. That one doesn't look like it would be all that hard to. That one doesn't look like it would be all that hard to evaluate by hand. But I don't want to carry out the evaluation because that's not the key part here. Wait, let me open. Let's go back. See if I can find it. Oh, let's look at this volume. Let's see if we can set that one up as a. See if we can set that one up as a triple. So here's a triple in that represents that volume. So the way I figured that triple again was by looking at these horizontal discs. Notice as you're going from top to bottom here, that volume is just a bunch of these horizontal discs, right? So I tried to calculate the area of each one of those horizontal discs from top to bottom there and then integrate them together. Of course, what's difficult is those discs are not all the same size, right? Okay, they vary in size depending on value of z, correct? So if you try setting up an integral with that idea, you get this integration. But we can do it easier, I think, because remember, what sort of volume is this? This is a volume beneath a surface, right? Down to a region in the XY plane. So we can set this one up more easily, okay? Because it's a volume beneath a surface, this surface, down to a region in the XY plane. Here's that, there's that region in the XY plane. Looks like this. By the way, how did we find that, how did we find that region in the XY plane? So how do you find the trace in the XY plane of this object? Yeah, by setting z to 0, right? And setting z to 0, right? And then looking at that equation. And when you do that, you get x squared plus 2y squared equal 4. Okay. And so we were able to figure out, oh, the y-intercepts were 2 and minus square root of 2, right? Okay. And x, these two curves, the curve on the left and the curve on the right, would be plus or minus the square root of 4 minus 2y squared. So this picture is the same as this disk down in the XY plane. But that is the region in the XY plane above which volume, right? But the volume beneath this surface down to this region. Down to this region. So this one we can set up the triple integral in that sort of shorthand fashion that I was showing you a moment ago. So let's see, what would that look like? Remember, use dz first. Let's use then dx dy, but we could do dy dx. So what are the limits on z there? Not quite, right? Remember, you go from 0 up to what? Your surface. But what's the formula for this surface? It's right here. So you go from 0 to 4 minus x squared minus 2y squared. So 4 minus x squared minus 2y squared. Now, what about for x? Well, I can see it in this picture where I've drawn the region of integration, right? We want x to start at the left hand of this. This is an ellipse up to the right hand of this ellipse. So that means x is going what, from this curve right on the left to this curve on the right. There are the formulas for those curves. I found that again by setting x to 0 and setting z to 0 and solving for x. So you're going from what, the square root minus the square root of 4 minus 2y squared, right? Up to square root of 4 minus 2y squared. And now y is the easy one, because what's y going to from? Yeah, minus the square root of 2 up to positive square root of 2. Oh, so this this triple area. This one's much easier to think about than this one. Oh, we just have a time. Our timing is good. I want to go back to let's go back to the homework. let's look at the last couple of problems in the homework and at least see if we can set them up. Even if we don't try, maybe not try doing the evaluations, but let's see if we can set them up. So here we want to use a double integral, but we're not computing the volume, just computing the area of this shaded region. That curve, by the way, that's called a cardioid. That's what that shape is referred to. Cardioid. So we want to find just the area of that cardioid. Okay. So that's kind of a challenging area to find, right? Because that's not a standard geometric shape, right? So find that. So remember, what is that? Since we're looking for area, what's the idea here? We're going to use a double integral, but what's going to be the integrand, right? Yeah, so we just get a simple integrand there of of 1. Y'all remember that curve, 3 plus 3 cosine theta. See if I can find some blank paper here. 3 plus 3 cosine theta. There's plenty of it. So we're going to use a double integral. And integrand of 1. Remember, we'll use dr d theta, but in this case, in my integrand, what do I have to throw in? Yeah, 1 extra factor of r, right? So that's not necessary in the rectangular coordinates, but we need that extra factor of r here. And now all I need to do now, right, is see if I can figure out a way of describing that region in polar coordinates. Well, it certainly looks like. What about the limits on the r? Remember, if you have r equal 3 plus 3 cosine theta, you're right on the curve, correct? But we want points inside the curve also in our region. So how do we fix our equations? Yeah, just make it less than. That's typically what's going to happen. So that means r is going to be between 0 and 3 plus 3 cosine theta, right? You're looking for r values bigger than or equal to 0, but out to 3 plus 3 cosine theta. So 0 to 3 plus 3 cosine theta. And now, so the question, here's that darn question again. What does theta have to be? So what range do we want on theta to describe that entire curve? A good guess would be 0 to 2 pi, but we better test that and see what happens, because we don't want too large an upper bound here. If we do, we get a little bit too big an area. So let's test that in our polar graphing. So let's see, that was just theta, right? And but it was 3 cosine theta, right? But then here we had a 3 and a plus. 3 plus 3 cosine theta. And see, that gives us a little bit of the cardioid, right? But I don't have the proper bound. So let's try, let's just try 1. See if 1 pi is enough. And not quite. That's half of the cardioid. Okay. So here our standard choice looks like it might be the right one. Oh, there we go. Okay. I think it's that one is kind of obvious because here you only have cosine theta, right? And what's the period of cosine? Without any multiple here, it's 2. So that kind of gives it strong. Nice. All right. So the rest of this is just, the rest of that now is just evaluating that double integral. I don't think that one's not too bad. Let's try the next problem. See if we can at least set it up. Oh, wow. So here we still want an area, but we want area bounded by graphs of these equations. So they're telling you one of these things is a circle. That's 3 cosine theta is a circle. And then this equation, which is another cardioid, another one of those heart-shaped ones. But we want the region between those two graphs. So really need to see that to understand that region looks like. So you're going to get two curves, and we want between those two curves. So let's try plotting those, because otherwise we're not going to have any hope, right? We know one of them is a circle. Was that 3 cosine theta? Was that what it was? Ah, so there's a circle. So they were right about that. And let me add one here. So what was the other one? R, whoops. Was it 1 plus something? 1 plus cosine theta or something? What did I do? If I just spell out the words theta, the letter theta, it will. Oh, okay. So I do see a cardioid for the second one. So they say reach in between. Man, that gives us lots of here. I do this part, this little piece, and this piece, or it could be, or they overlap right there. So that, or is it this crescent piece outside? I think, I think it's the crescent on the outside is what. That's not the inside. What the area that kind of core blue shape between this curve, between this curve. So I'm thinking I'm thinking, see. So is there some way I could figure out how to describe this? See, between this curve and this curve, that, what about the radius of those points from this curve to this curve? I think they have to be less than or equal to the circle, right? But what's the equation for the circle? Was it 3 cosine theta? So you want them less than or equal to 3 cosine theta, but you don't want them inside the cardioid. What was that? 1 plus cosine theta? So I think you want them between 1 cosine theta, right, and 3 cosine theta? Between 1 plus cosine theta and 3 cosine theta. That's what you want. That's the thing. Let's try writing that. Let's try writing that much down so we can remember what we started with, right? So we have our double integral. It's going to be 1 times r again, dr d theta. And I think we want our r to be between the cardioid, which is 1 plus cosine theta, up to the circle, which is 3 cosine theta. But the tricky part is, the hard part is, what is the angle? What is what are the angle is in polar coordinates these two. So notice you want that angle to be, I can almost see it here. Want that angle above this, right? But below this. So yeah, it looks like between pi over 3 and minus pi over 3, but I can, because this is minus pi over 3 if you look on the polar graphic. Angle down to this point is minus pi over 3. It's just symmetrical up, so it's up to pi over. So it's the angle between this line and this line. So I'm guessing that's the right limits. Let's write those down. So we think this is minus pi over 3 up to positive pi over 3. But if you weren't looking at is there any way you could figure that out without any way you could figure that out analytically? Pencil and paper? Didn't have the nice polar graphic paper where we could go on. What are what are these 2 points? Here and here. They're the intersection points of the 2 curves, right? Yeah, set the 2 curves each together and see what we can figure out from that. So when we set those equal, let's see, it's these 2 things, right? We want to set equal to each other. So we have 1 plus cosine of theta, right? Equals 3 cosine of theta. See if we can solve that equation. So that looks like 2 cosine of theta is equal to 1, which means cosine of theta is what? 1/2. And where is cosine of theta? 1/2. Well, one of them is pi over 3, but also what? Negative pi over 3 as well, right? Okay. So also at minus pi over 3. Oh, so we could see it from the equations. There are the I wonder if I wonder if I change. Wait, let's change this. So when we're plotting these, let's change this from, what did I say, pi over 3? We're running out of time. Oops, almost. Pi divided by, where's my pi? Pi divided by 3 up to, this is minus. And then positive pi divided by, spell pi right. Oh, yeah, that gives me hope. You see how that changed see how that changed the, yeah, perfect, right? Those limits. All right. Okay. Well, we've exhausted ourselves, right? We're out of time there. Okay, so remember, right, for the test on Monday, problem 10, right? So, on the test Monday, you won't have polar coordinates or triple intervals. But we'll save that for the final exam, and the solutions for the sample are, so that's problems 1 through 10 on the sample, not the last 4 problems. I think so not the last 4 problems. And what else I was gonna oh yeah, so the answers are posted, but I will have a little video just with some of the explanation of some of the solutions, some of those problems, and should be tomorrow or Friday. Will be posted in that sample test folder, but I'll send it out via WebAssign. Right. Okay. Very well. I'll see you guys on Monday.